So I will be sending you the solutions for worksheet 6, and you have to prepare only the type of simple integration problems in worksheet 6 for the upcoming test on Sunday. Okay. So we'll start with a quick review of basics of integration that we discussed last time. Let's start by understanding once again the process of indefinite integration. So indefinite integration is an operation that is used to calculate the antiderivative of a given function. So when we perform the operation of integration on a particular function, it gives us another quantity which is called the antiderivative. Of the function fx. So the fact that it's antiderivative, it means that if we differentiate ix, then we get the original function fx. So for example, as we can see that if we differentiate x square plus any constant, we get 2x. So that means x square plus c is the antiderivative of 2x. So this means that if we integrate the quantity 2x, we will get the value x square plus c, I guess. So this is the simple meaning and interpretation of the term indefinite integration. So this symbol means indefinite integration as an operation. On performing that operation, what we get as the output of the operation is the antiderivative. So it is the reverse process of differentiation. Then after this, we saw the basic formula for integration of any power of x to the power n. This is given by the formula x to the power n plus 1 divided by n plus 1 plus c. This formula is applicable for all n other than minus 1. So n can be any real number value other than minus 1. The exception case for n equal to minus 1 is given by the formula ln x plus c. You can see. Okay. Okay, and then we had seen the properties of integration. But integration of a constant is a linear term. Okay. Then integration of a constant multiplied by a function is constant times integration of the function, and integration of the sum or difference of two functions can be split like a distributive property as the sum or difference of the individual functions. So this is all that we've learned about integration till now, and next we will do some example problems based on this, similar to the questions I have given in worksheet 6, and that is the level of questions you have to prepare for the test coming up on Sunday. Okay. So let's work out some practice problems and then we'll move on to the next level of integration problems. Okay, so work out the following integrations. Okay, so please work out the following four integrations and send me the text message with the answers. Yes, very good, Caleb, that's correct. Yes, Adinath, correct, very good. Rishabh, check the algebraic sign of your answer first once. No, Anand and Raghu, please check your answers. Yeah, Adinath, correct for the second one. Okay, people, not all the answers I'm getting are correct. So I'm just putting up the answers, verify it. I will give you the methods in just a moment. So this one's answer should be minus 1 by x plus constant of integration. This one's answer should be x square by 4 plus 1 by 2 times ln x plus c. Okay. This one's answer should be plus c. Yeah, Siddharth, your answers are correct. Very good. Just have to add the constant of integration in all of them. Okay, so let's verify the steps for each of these questions now. So you have to be able to apply these steps and the so basically the steps come from the properties and the basic formula that we've seen above. So for example, for the first one, dx upon x square. So what you have to do is you have to express this as a power of x in the numerator and then apply the formula x to the power n plus 1 upon n plus 1 plus c. So as you can see, that becomes minus of x to the power minus 1 plus c, or you can just express it as minus 1 by x plus c. And the nice thing about integration is once you do it, once you get the final antiderivative answer, you can always check yourself by differentiating this. You can check it that if you differentiate this, you should get the original function which we integrated. So differentiation of minus 1 by x is minus 1 into minus x to the power minus 2. So it's 1 by x square. That's correct. That is what we had started with, the integration. So that shows you, that verifies that the answer is correct. Okay. Similarly, the second one, you have to just simplify it a little bit first, okay, before we can. So separate it out into two terms. Yes, any doubt? Okay. So this becomes x by 2, okay, plus 1 by 2x. Now we can use the distributive property and also bring the constant outside. So 1 by 2 times x dx plus 1 by 2 times 1 by x dx. Okay. So now apply the formula for this one. So x square by 2. Okay. And this is, remember, the exception case, 1 by x. So it's ln x. Okay. And you can write a combined constant for the two of them. Okay. Because this integration will give us a constant, the second one will give us a constant. but the constants can take any arbitrary real number value. So you just add them and write a single constant c. So finally our answer becomes x square by 4 plus 1 by 2 ln x plus. Okay, similarly, the third one now. Okay. So again, we can simplify it and first write it as a single power of x and then apply the formula. So further solving this, or you can even write it like this: 2 by 7 times x cube root x. So this is an optional step.
Sir,
X, yes.
sir, x square root x will be x raised to 3 by 2, right?
No, x square into root x beta is x to the power 2 into x to the power half, no? So 2 plus half is 5 by 2. Got it?
Yes, sir.
Sir,
Yes.
in the bracket it should be x raised to 5 root 2, right? X raised to 5 root x.
Which one?
Sir, the final answer.
This x cube root x.
Yes, sir.
No, see, x to the power 7 by 2 is correct, no? You got up to this?
Yes, sir.
So 7 by 2, when you split it, how it's split? It's 3 plus half, no?
Yes, sir.
So it's x cube into x to the power half. So it's x cube root x, beta.
Yes, sir. And
Got it, no? Okay. And the final one just involves a little bit more solving. We have to expand the term in the whole square, right? So that we can express it as a polynomial, right, inside. So a square plus 2ab, right, plus b square. And now we can use the distributive property and split this. And that will give us the required answer. Okay, and the thing is, always if you have enough time during a test or something, you can even check your answer by differentiating the antiderivative that you got, and that should give you the integrand or the function that you are integrating. Okay, so hope all this is clear to all of you. Let's move on. Now the next thing we will see is the formulae for the trigonometric, basic trigonometric functions. So the sine and cos terms are pretty easy. Okay, integration of sine x, logically it will be minus cos x. Okay, because so plus c, because we know that differentiation of cos x is minus sine x. So therefore we know that differentiation of minus cos x plus any arbitrary constant will be sin x. So this is the simple logic for this first formula. Okay. Similarly, integration of cos x will be sin x plus c, because we know that differentiation of sin x is cos x. However, the next set of integration formulae are a little bit more complex. This is given by ln of sec x, or natural log of sec x plus c. And the logic of this is very simple. You can see that if you differentiate ln sec x term, okay, you have to use the chain rule for differentiation of this. So 1 by sec x into differentiation of sec x, which is sec x into tan x. Okay. So that will give you tan x. So that is the logic of this third one. Similarly, the reciprocal ones are again a bit complex. Like, for example, integration of cosec x is given by the term ln, so it's given by minus of ln cosec x plus cot x. Okay. Again, you can understand the logic of this by differentiating this term. So it's minus of 1 upon cosec x plus cot x into differentiation of cosec x plus cot x. Now remember, differentiation of cosec x is minus cosec x cot x, okay, and differentiation of cot x is minus cosec square x. Okay. So this becomes, if you take minus cosec x common in the numerator, we are left with cosec x into cot x plus cosec x. Okay. So that reduces to cosec x. So it's a bit lengthy, the logic of this formula. So, but anyhow, so this is something that you have to memorize. The indefinite integration of each of the 6 trigonometric ratios or trigonometric functions. Okay. So similarly, this becomes ln sec x plus tan x. Okay. And you can see the verification yourself later. And the final one, so therefore this can also be written as ln sin x, because minus of ln cosec x is ln of 1 by cosec x, which is ln sin x. So these ones are all a little bit lengthy and complicated to memorize. You have to just find a way to keep them in mind. However, looking ahead in our physics applications, the most important one of these in future chapters are going to be these two.
Sir,
Yes.
Sir, can the integral of tan x be written as minus ln cos x?
Yes, it can be written like that also. That's correct.
Okay, sir.
Okay. And the final one, as far as basic formula of integration goes, exponential function. Now this one is very easy because we know that the differentiation of exponential function is e raised by x itself. So integration is also the same. So you can say that these are the 8 or 9 basic formulae. The x to the power n formula, okay, with the exception n equal to -1. Then the 6 trigonometric functions and the exponential function. These are the basic formulae of integration that you have to keep in mind. Most of these formulae are very simple to keep in mind, just as a reverse of differentiation. But few of them, like these 4, for example, a little bit lengthy. So you have to just make sure that you remember them. Okay, now having done all this, we come to our first method of integration, which is integration by substitution. So in many ways, we can say that this is the equivalent of integration that we saw chain rule in differentiation. So chain rules equivalent in integration is called integration by substitution.
Sir, can you please say exponential function?
So there are many different types of substitutions that can be done, but we'll start with the first one, which is a very simple type of substitution. That is, whenever we have to do substitution of a linear term. So I'll just express it with an example, then we'll make a generalization of it. So suppose we were integrating square root of something like this, 2x plus 1, which is a linear term. So you can see over here that 2x plus 1 is a linear term. Okay. Now we know how to do integration of root x. This we know is how much? It is 2 by 3 x to the power 3 by 2 plus c. So how do we do this integration now? So that is where the substitution step comes in. We substitute that linear term 2x plus 1 as some dummy variable. So then this term becomes simple, it becomes root z, but then dx also has to be replaced in terms of z. So next thing you can see that if z is equal to 2x plus 1, then dz by dx is the differentiation of 2x plus 1, which is simple, it is 2. So we can cross multiply and we can also replace dx with dz by 2. So now if I substitute in the integration the value of dx as dz by 2 and the value of 2x plus 1 as z, then it becomes a simple integration of this type, which we can carry out. Okay. So that is the basic idea. Okay, Akshat, I'll take you back to the exponential function, but let's finish this first. Okay. So finally, on doing this substitution step, this integration can now be expressed as replace 2x plus 1 as z and replace dx as dz by 2. And 1 by 2 is just a constant in the integration, so it comes outside. So now refer to this formula above, and this just becomes 1 by 2 times 2 by 3, z to the power 3 by 2 plus c. And then one more step we have to do, which is just a resubstitution step. So z is a dummy variable, so we have to remove it. So finally it becomes 1 by 3 times z, which is 2x plus 1, whole to the power 3 by 2 plus c. And you can always verify that if you differentiate this by chain rule, you'll get square root of 2x plus 1. So finally that becomes our answer. Okay. So this is an example of the application of this type of substitution. Substitution of a linear term, okay, which is the most basic type of substitution. Okay. But also most often we are doing a substitution, it's going to be a simple basic substitution like this. Okay. So just make a note of this example. Okay. And when you're done with the note, you can also verify this, that if you differentiate this term, so by now you've done enough practice of chain rule. So you can do this verification directly like this. It's 1 by 3 into 3 by 2 into 2x plus 1 to the power half into differentiation of 2x plus 1, which is 2. So that will give you square root of 2x plus 1, which is correct. Okay, so this is the whole process actually. Okay, with this example we've understood it. Next we'll generalize it for any given type of function, how we use this. And we'll in fact make a shortcut formula of it. So just make sure you understand the steps that we have done here. Let me know if there's any doubt. Yeah, Raghuram, the substitution step here is that, see, the linear term, it's the square root function, but inside the square root, instead of just x, we have the linear term 2x plus 1. So we substitute 2x plus 1 as a dummy variable. Okay, so that term becomes root z. But in the integration, we can't just write root z and leave the dx that way. Okay, because we can't integrate z with respect to x. No? So the
Yes,
dx term has to be replaced in terms of dz. So for that, now we have to find dz and dx's relation. So how that comes? That comes by differentiating this substitution term. Z is equal to 2x plus 1. So dz by dx is how much? It's 2.
yes, sir.
Is it clear? Yeah. Okay.
Okay, sir.
So now you just cross multiply. No? So if dz by dx is 2, okay, that means a small change in z divided by a small change in x is equal to 2. So cross multiply. So dx is half of dz.
Okay, sir.
So both the things have to be substituted. The linear term has to be substituted with z, and dx has to be substituted in terms of dz. Then only we can complete the integration.
Okay, sir.
At the bottom where you have verified it,
Yeah,
it is
yeah.
written as 1 upon 3 is into 3 upon 2 into 2x plus 1 half into 2. From where did 2 come?
Chain rule, na beta.
Okay.
See, it is some function to the power 3 by 2, na?
Yes, sir.
2x plus 1 to the power 3 by 2. So when we differentiate that, it is n into that function to the power n minus 1 into differentiation of that term 2x plus 1. So differentiation of 2x plus 1 is 2.
Yes, sir.
Okay. Okay, so hope the steps are clear in this. Now, so what we'll do is we'll make a generalization of this. Acha. Before that, I'll just go back to this earlier set of formula. In case anybody has some part to write down in this, you can compute that.
Thank you, sir.
Okay. So this process that we have done for this particular example, we can now make a general formula out of it. Okay. So if we are doing an integration of this type, so the function that we are integrating, it applies to a linear term. Okay. So this type of thing. So for example, we have, let's say, ax plus b to the power n. Okay. Or we have exponential of ax plus b. Or we have any trigonometric function like sine, cos, etc. of ax plus b. So this is the kind of situation we are integrating. Okay. So for this, what we will do is we will substitute ax plus b as z. Okay. And therefore, dz by dx is differentiation of ax plus b, which will be equal to a. Okay. Of course, it is understood here that a and b are constants. They are not variables. They are constants. Okay. Okay. So having done this, now we substitute this in the integration. So integration of whatever function becomes integration of f of z. Okay. Oh, before that, so this step now means that if we cross multiply, dx is equal to dz divided by a. So this thing and this thing have to be substituted. So fz into dx. Now dx is dz divided by a. So 1 by a integration fz dz. Okay. So next step, we carry out this integration, whatever it is, and so it is equal to the antiderivative of f. So it will become iz plus c, where iz is the antiderivative of fz. Okay. And finally, on resubstitution, so remove the dummy variable. Okay. So this integration's answer, okay, comes out to be like this: 1 by a times antiderivative, but applied to ax plus b instead of x. So this becomes our answer. Okay. So from this point onwards, we can use this as a direct formula. So instead of doing all these steps, we can use this as a direct formula. Okay. So for example, I know that integration of e raised power x is e raised power x plus c. So therefore, I know that integration of e raised power, let's say 5x plus 2, will just become 1 by 5 e raised power 5x plus 2 plus c. I've just applied this formula over here. So I don't need to do all these steps every time. I can just use this as a direct formula. So make a note of this and understand the steps that I've used in the general formulas derivation, and then we'll see some examples of application of this. Okay, so let's pick up a couple of example questions. Okay, so this is all very simple. As you can see, you have to just do the substitution, or not even the substitution, you have to just apply the above formula. So just work these out. I'll put up the answers in a minute. Yes, Adina, that's correct. Anand, correct. Akshat, there's a minus sign. Okay. So I'm just putting up the answers on the side here. Okay, so with this we can see that more types of functions can be integrated quite easily. So now let's look at a couple of simple application questions of integration, indefinite integration, in physics type of situations or different maths type of situations also. For example, I'll take you back to a question we had done in worksheet 2. Now we can use integration instead in that. There was a question like this, that y is a polynomial function such that there was some information given about the derivative of y. First of all, dy by dx was ax square plus bx plus c, and y was equal to 0 for x equal to 0. Okay, y was equal to 6 for x equal to 1. Y was again equal to -1, 0 for x equal to -1, and dy by dx was equal to 2 for x equal to 0. So we wanted to find the unknown constants a, b, and c from this. Okay. So this type of question we had done at that stage by sort of a backward calculation. Okay, what we had seen there is that dy by dx was a quadratic function. So we had logically understood that that means that y is a cubic function. Okay. It's a polynomial of degree 3. So we assume so y was some kind of cubic function. So we said about this and we then solved further. Okay. Now here today we will do it by a more direct method. We'll directly use integration. So that basically means that if dy by dx is given to us as a function, okay, that means y is the antiderivative of that function. Because we know that this implies this only. So basically we'll understand this, that dy by dx is equal to ax square plus bx plus c, where a, b, and c are constants. That means y is integration of ax square plus bx plus c. So this further means that y is equal to a by 3x cube plus b by 2x square plus cx, plus we'll have to introduce another constant here, so we'll write it as c1. So c1 here is the constant of integration. Obviously, as part of the question, it was understood here that a, b, and c are constants which have some numerical value, which we wanted to find out. Okay. So now the thing is how we'll find the values of each of these constants a, b, c, and c1 by using these conditions. Okay. So now we have to find not only a, b, and c, but also c1 to solve the problem entirely. Okay. So next, what we have to do is we have to solve for and for that we have to use each of these conditions which are given. Condition 1, Okay. So if we substitute each of these conditions in this given term now, so we can see, for example, from condition 1, we'll get that y is equal to 0 when x is 0. This will tell us that c1 is equal to 0. Okay. Then second term, when we substituted, 6 will be equal to a by 3 plus b by 2 plus c. C1 we already know is 0 from above. So we have this equation that a by 3 plus b by 2 plus c is equal to 6. Okay. And from the third condition, we have again 0, but a by 3 into x cube, so that's minus 1, plus b by 2 into x square, so that's 1, plus c into x, which is minus 1. So we have this, that minus a by 3 plus b by 2 minus c is equal to 0. So if we just add these two equations, we will get d is equal to 6. Okay. And then if we substitute the fourth condition, so we have dy by dx is 2 when x is 0. So we directly get that c is equal to 0. So now we use this result, okay,
So
along
C
with,
is
let's
equal
say,
to 2, right?
this one. Sorry?
C is equal to 2.
Yeah. Sorry, c is equal to 2, my mistake. C is equal to 2. So if we use this result along with, for example, this equation, so minus a by 3, okay, plus b by 2, so b is 6, so plus 3 minus 2 is equal to 0. So we're getting the value of a as how much? We're getting the value of a as 3. So now we've got the three unknown quantities. We've got a as 3, b as 6, c as 2. So we got y as a by 3 x cube, so that's x cube, plus b by 2x square, so that's 3x square, okay, plus cx plus c1, which was 0. Okay. And therefore dy by dx is 3x square plus 6x plus 2. Now see that these two satisfy all the four equations we had written above. So it's still a bit of a lengthy question because there are a lot of substitutions, but you can see that it has become more direct in the solution. Instead of doing this guesswork, okay, that dy by dx is quadratic, so y is cubic, so assume some coefficients p, q, r, and s, and then solve that way. We can directly integrate dy by dx to come up with y in terms of ABC, and then we can put the conditions which are given. So this is a maths example of an application question involving integration. Next, we'll see a physics type of situation also. So in physics, differentiation is used when we have a rate of change type of situation. Okay. So integration is used when we have an opposite of rate of change kind of situation. Okay. Or anti-derivative kind of situation. Equation number 4, beta, Rishabh, it's come from this. This is given to us this condition that dy by dx is 2 for x equal to 0. So you substitute in this now. So put the left hand side as 2 and right hand side put the value of x as 0. So we get
Yes, sir. Yes.
Okay, so next up, let us look at a physics type of problem involving the application of integration. So let's look at an example from a kinematics kind of situation, okay, which is in fact going to be the next chapter we'll do anyway. So after we complete integration. So it is given to us that a particle moves along a straight line with variable acceleration. So it's not a uniform acceleration such that that variable acceleration is given by this relation, let's say. Okay, so it is 2 plus square root of t, or let's say it is 2 plus 2 times square root of t, where acceleration is in meters per second square and t is time in seconds. So if its initial velocity was u equal to, let's say, 3 meters per second at t equal to 0, find its velocity or its instantaneous velocity as a function of time. So this is going to be a very routine type of application of calculus or integration we'll see in the next chapter. So here what we'll do is we'll just make use of the definition that acceleration is defined as the rate of change of velocity with respect to time. So that means the calculus definition of instantaneous acceleration is that it is dv by dt. Okay. So just use this. So try this out, people. So you can imagine that this is a kind of situation where we have some kind of variable force which is acting on the particle. So therefore, the force is increasing with time. So accordingly, the acceleration of the particle is also increasing with time. So that can create a situation like this where it has a non-uniform or variable acceleration. Now, if you interpret it like we did in the last question, that acceleration is rate of change of velocity. So dv by dt is this known function 2 plus 2 root t. So v should be what? It should be antiderivative of this. Okay, so let's solve this. So as I said, we'll use the relation that dv by dt is equal to a, which is this function. So that means v should be equal to integration of a dt. So v should be equal to integration of so now we have to find the unknown constant. So this is v such that u was given to us as 3 at t equal to 0. So substitute that. So 3 should be equal to so the value of the constant of integration is 3. So the instantaneous velocity at any point of time t is given by this. As a function of time, where v is in meters per second and t is in seconds. Okay. And you can also just verify that this also means that if you differentiate this, you'll get this was the acceleration we had started. Okay. So it verifies that what we had found out is the correct value of instantaneous velocity corresponding to the given value of instantaneous acceleration. So see how we eliminate the constant of integration over here, because some other physical condition is given to us that the initial velocity. So we had to make use of this condition. Okay. Otherwise, the constant of integration would not get resolved for us. It would have remained an unknown constant. But because this condition was given, from this we are getting the fact that the constant of integration is 3. Yes, very good, Parv. That's correct. Akshat, correct. No, Anand, we cannot use v is equal to u plus at, because the condition for using v is equal to u plus at is that a must be uniform. Remember, every equation or every formula that we use in physics has some precondition to it, and the precondition for this particular formula is that a should be uniform. No? What will you substitute as the value of a over here otherwise? Because we can see that a at a time of 1 second is 4. A at a time of 4 seconds is 6. Right? A at a time of 0 is 2.
Yes, sir,
There's,
got it.
there's no consistent value of a, no? So we cannot. Okay, so this is the type of situation which in future chapters we will see application of integration. Okay. Now with this we come to the, so that was about indefinite integration. Now we'll also take an introduction into the second type of integration today, the second operation in integration, which is called definite integration. So indefinite integration was an operation that gave us antiderivative. Definite integration is an operation that gives us a different situation. Okay, it is an operation used to calculate the area subtended by the graph, okay, or curve of a function y is equal to fx between the limits x equal to a to x equal to b. Okay. So the purpose of this operation, definite integration, is to calculate this kind of area. If a function, when we plot the graph of it, the function's graph is a curve like this, let's say. And we want to calculate the area that this curve subtends between, let's say, these 2 points A and B on the x-axis. So that means we want to calculate this area. So this area will be calculated using definite integration. So the symbol of definite integration will be like this. Integration of fx, but with two other terms written below and above. And these are called the limits. So this whole symbol is read as definite integration of fx from x equal to a, which is called the lower limit, to x equal to b, which is called the upper limit. In short, we can also just write it as e to b of x. So whenever the integration symbol has values below and above, or what we call limits, then we know that the operation is no longer indefinite integration. The operation we are doing is definite integration. And definite integration does not give us antiderivative. Rather, it gives us a numerical value, which is equal to the area calculated. Now we'll see how to do this calculation next. Okay, but first let's understand the meaning of the operation. So that is this. Okay, so let's see next how we calculate this integration. So the idea is that if we know the indefinite integration of this function is this antiderivative, then the value of the definite integration is given by the value of this indefinite function at the upper limit minus the value of the indefinite function at the lower limit. Okay. So as a simple example, let's understand. If we want to do integration of, let's say, cos x from x equal to 0 to x equal to pi by 2. Okay. So that will become sine of pi by 2 plus c minus sine of 0 plus c. That will become 1 minus 0 of 1. If we want to do, for example, integration of x square from x equal to 1 to x equal to 2, so that will become 2 cube by 3 plus c minus 1 cube by 3 plus c. Become 1 by 3.
So if we are calculating the area, then what is the unit?
Sorry, better. What is the doubt again?
So if we are calculating the area between the upper limit and the lower limit and that space, then what is the
Yes.
unit of the answer
What's-
we get?
Little bit louder, please, better. Can't hear you.
So what is the unit of the answer we get?
So the unit of the area will be whatever the unit is on the x-axis multiplied by whatever the unit is on the y-axis. So at the moment we are treating them like just numbers, so it's unitless. Okay.
Okay, sir.
But for example, if your x is in time and y is in, let's say, meters per second, so then your area will come in meters because it's seconds into meters per second. Understood? No? So sometimes to make the writing of this easier, we can introduce an intermediate step that what you do is you first calculate the indefinite function and on that you substitute the limits. Okay. So for example, if I'm doing this, so first what I'll do is I'll calculate the indefinite integration. And on that I'll put the limits. Okay. And then you need not write the constant also because it cancels out. So as you can see, this is 2 cube by 3 minus, oh my mistake. This is 2 cube by 3. Na? So it will be 8 by 3 minus 1 by 3. 7 by 3. So this intermediate step just makes it easier to work it out. So note this down and let's try some questions. Okay, try out these 3 or 4 questions we'll discuss.
Sir, on the
Yes.
right hand side, what does that line represent after I of x?
That line represents that it's a definite integration. So we have to put the limits in the indefinite. That we have to substitute IB minus IA. Understood, no?
Yes, sir.
Okay, so I'll just put up the answers first and I'll verify them for you. So this should be 1, right? This should be 2. Okay. Should be 12. And right now the area is not given in any unit because we are considering X as a number and not a physical quantity. Okay, but so very good, Maitri, correct for all 3. Pratyush, good. Adinath, correct. Anand, correct for 2 of them. Yes. Parv, correct. Very good. Okay, so first one, so let's first find the indefinite integration, which is minus cos x. But on that, we have to raise the limits 0 to pi by 2. So the upper limit value will be minus cos pi by 2. Okay. Minus the lower limit will be minus cos 0. So this becomes 0 minus of minus 1. That's how we get 1. Okay. And also we can understand the interpretation of this, that if you visualize the sin x graph, you can see a very interesting aspect of it that will come out using these 2 parts. Okay. If we plot y is equal to sin x, then this is how one complete cycle looks like from 0 to 2 pi. But also, sorry, yeah, also pi by 2 is this point. So notice that the sin x graph has a symmetry, like an inverted symmetry, that this half and this half are the same. So whatever area we are getting here, this is actually integration from 0 to pi by 2. But next step, we'll see that this area is actually equal to that area. This area is pi by 2 to pi. And as it turns out, this is also 1. So that is why the total area from 0 to pi will come out to be 2. And this, the steps are a bit tricky. So to make sure that you don't make any mistake with the algebraic sign and all when you are substituting. So it's minus cos pi, minus of minus cos 0. So it's minus of minus 1, minus of minus 1. So that's how we get 2. So that is the interesting thing about the symmetry of the sin x graph. Okay, and let's come to the third one finally. So 2 to 4. So the indefinite integration is x square plus c. So the upper limit will become 16, the lower limit will become 4. Difference is 12. Okay. Now this one also, for example, if you visualize the graph, you can actually calculate the area using geometry because it's a straight line graph. And you can verify that geometrically also you would have got the same area that we are getting by integration, which is a sort of nice way to verify that definite integration indeed works and gives us the correct value of area. So the graph of the function y equal to 2x, it's a straight line, right? So it will passing through the origin and all, so it will look like this. Now at the point x equal to 1, the value of y will be 2. And at the point x equal to 4, let's say here, the value of y would have become 8. Sorry, I wanted at x equal to 2. This is 4. So now I want to calculate this area. Okay. So this shape is a trapezium. It's area of a trapezium. And the shape of that trapezium, I'm repeating it above here, you can see it's like this. Okay. So this height, this side is 4 units, this side is 8 units, and the perpendicular distance between these two sides is 2 to 4, which is 2. So this area of trapezium should be half into sum of parallel sides into distance between them. So it's 12. You can see that it's verified to be the correct one. Okay, people. So hope this final part is also clear by the geometrical method. So this is just a side. Of course, we have to calculate the area by integration, but we just verified that in this particular case, we can also show geometrically that that particular area is the same value. Now this gives us a lot of confidence because see, though we have sort of verified the value of the area only for a linear function, okay, but the whole idea of calculus is that if you have any curve for a general type of functions graph, if you split the curve into small sections like this, they're all small line segments. Okay, so what works for an extended line segment like this will also work for a small section of that line because of the same logic. And then we extend that logic to section after section. So it should work for the whole area. Okay. So we will see through this kind of process in the next class, okay, how we can actually show that it indeed gives us the correct value of area by this particular process. Okay. So with this, we conclude today's session. Next lecture, we will look to complete integration, and following that, we will move on to the chapter of kinematics, which will feel very natural for you because kinematics is like the first part of kinematics is a direct application of calculus itself. And second part, when we come to two-dimensional or three-dimensional motion, it's an application of vectors and calculus put together. So it will just feel like a very natural extension of what we have learned so far in physics. Okay. Anyhow, so make sure you prepare for the test on Sunday properly. Remember what we've done in today's lecture. You don't have to prepare for Sunday's test. Okay. No substitution based integrations, no definite integration, only the simple direct integration based on the first set of formulae that we learned last week. So make sure you do worksheet 6 completely. I will send you the solutions by tomorrow or day after. Okay. And also do a thorough revision of at least worksheet 3, 4, and 5. Okay. Particularly worksheet 5 and also worksheet 6, because maximum minima is going to be an important part of this chapter coming up, this test coming up. Okay. And with that, I think you should not have any difficulty scoring good marks in this portion at least. Okay. So wish you all the best, people. That's it for today's session. Thanks for attending and have a nice day.
Thank you, sir.
Thank you.
Thank you, sir. Bye.
Okay, bye.
Thank you, sir.